Now what we have here is steam, which is the working fluid in an ideal Rankine cycle. Okay, we have saturated vapor, which is entering the turbine at state 1, and it's entering at 8 MPa, 8 megapascal, which is 80 bar. Now, the other thing we have been told is that this is state 1. The other thing that we know is that the saturated liquid is exiting the condenser at 0.08 bar. So we know the exit state of the condenser, which is this. It's saturated liquid at 0.008 MPa or 0.08 bar. And this is where it looks on the TS diagram. The net power output of the cycle is given. It's 100 megawatt, which is good. We need to determine a couple of things. We need to determine the thermal efficiency, the backwork ratio, the mass flow rate of the steam, and lastly, the thermal efficiency of a Carnot cycle operating between the same temperature limits. Now, the part D, well, we know that the efficiency for Carnot cycle is going to be higher than the efficiency that we get in part A, right? But the question is, how much is the difference? How far are we from the Carnot cycle? That's all what we want to determine, right? And that's why I have included part D here. Now, before we go ahead in this problem, I just want to get an idea. Does everyone have textbook? I mean, the guys who do not have the textbook, please raise your hands. I want to see how many of you don't have the textbook yet. Okay, so about 6 students out of 33 do not have the textbook. So has the university provided you any information about when can you expect to get the textbook, or what exactly is the status?
I think they will distribute it this week because I just received my books yesterday.
Okay, that's good news. All right, so inshallah you'll have the textbook pretty soon. So because you guys don't have the textbook, all the homework problems that we are giving are like we're just not giving the number, but also the problem statement. So we will continue to do that for some time. And yep. Okay, so if you have the textbook, it's good. The textbook has some really good example problems, some of which we will be solving in the class. All right, so let's get back to this problem then. Abdullah, you want to add something? Okay, I see your messages. Yes, hopefully you'll get the textbook soon as well. Otherwise, we'll ensure that we'll keep writing the problem statements. Okay, so coming back to this problem, let's start with part A, right? We need to go ahead and determine the thermal efficiency. Now, for determining the thermal efficiency, right? So we just said thermal efficiency is work output of the turbine minus work input for the pump divided by the heat input. Okay, so the work output for the turbine, as we just saw, is H1 minus H2. Okay, work input for the pump is H4 minus H3, and the heat input here in the boiler is H1 minus H4. So basically we need H1, H2, H3, and H4, okay, for enthalpies. So that's the first thing that you would need to determine, right? So the first step is basically to figure out all the properties at states, or specifically the enthalpies and at all the states. And for determining the enthalpies at all the states, we may need some other properties as well. So let's first look at this, right? So here, some states, determining the enthalpies or properties at some states are going to be easier than the others. So let's start with the easiest one. Let's start with state 1. We have information about its pressure, and we also know that it's saturated vapor, right? So we can, it's a very simple matter to go ahead and find its state, its property. So the H1 and S1 would simply be equal to Hg and Sg at a pressure of 80 bar. So you just go to the saturated pressure table, pick up the Hg and Sg values, and that's all you have for enthalpy and entropy. Now there's this very specific reason why we are bothering to find S1. You see, the process 1 to 2 is an isentropic expansion process, right? And we need to locate state 2, and we don't have enough properties about state 2. So the only thing we know for now is that the pressure at state 2 is 0.08 megapascal or 0.008 bar. Okay. Now we need one more property to fix that state. As we know from the state postulate, we need two independent intrinsic properties. So the other property that will help us identify the state 2 is the entropy, right? So since 1 to 2 is an isentropic process, S1 is equal to S2. So we know the value of S2 and we know the pressure. Okay. So with the help of these two properties, we will be able to locate state 2 and find out the enthalpy. Now the thing is, state 2 is a mixture, right? It's a saturated mixture. And for the mixture, we know that all the properties such as enthalpy or entropy, it can be simply be written as SF plus X times Sg minus Sf. Okay, same is the way for enthalpy, X2 times Hg minus Hf or Hf Hg minus Hf or Hfg. Now, the thing is, we have the value of S2 known. Okay, SF and SG can be determined from the property tables because we know the pressure. Okay, these values will remain the same for this pressure no matter what the value of X2 is. So now, having known everything, we can go ahead and determine X2 because we need X2 when we are trying to calculate S2, and S2 is what we want to ultimately calculate. So what we do is we make use of this relation between S and the entropy at state 2 and the quality, and we determine the quality here. We know S2, we know SF, we know SG, plug in the numbers, and we get this value for X2. So as you can see, X2 is about 67.5%, right, quality. It's sort of okay, not bad, but maybe we would want it to be slightly higher, right, just to make sure that the turbine blades are safe. They are still okay at this quality. We still have some amount of water, so not ideal, but sort of okay. Now we have X2, and we just don't want X2, we want S2 as well, right? So we need the enthalpy at state 2. So we just make use of this formula. Again, HF and HFG are known just from the knowledge of the pressure. We need to know the value of X2 to locate exactly what the enthalpy is, right? So we plug in the numbers and the HF, the HFG, the X2, and we get enthalpy at state 2. Okay, so that's great. Now we need enthalpy at state 3. Now enthalpy at state 3 is very straightforward. Okay, it's at the same pressure at state 2 and it's saturated liquid. So just talking about HF at the same pressure, right? So we're just talking about this value. So S3 will simply be 173.88, which is HF, which we already found when we were looking at determining the enthalpy for state 2. Okay, so 1, 2, 3 are done. Very straightforward, very simple. Now we need to determine the enthalpy at state 4. And as I mentioned, enthalpy at state 4 is a bit tricky. If you're lucky and if you have a pressure, like in this specific case where we are having P4 of 80 bar, and we know the and I mean for this 80 bar, I'm reasonably sure we have the compressed liquid table. So we have an entropy which S4 is equal to S3. You may be able to go to the tables and pick up the value of enthalpy. You may of course require some interpolation, okay, but it's sort of doable. But in most cases we don't have that luxury. Okay, the interpolations require quite a lot, and to avoid all the process, what we do is we generally make use of this reversible work input formula, for an open system. Okay, so the work input for a pump is simply equal to specific volume, which for state 3 is simply Vf at this pressure at 0.08 bar times P4 minus P3. Okay, and P4, P3, and V3 are very easy to determine. P4 and P3 are in fact given in the question. Okay, we already have H3, so then we can determine H4 from this equation. So we can write H4 as simply H3 plus the work input to the pump, and work input to the pump is given by this formula right here. So it's a matter of plugging in the numbers now. You just have to be careful when you plug in the numbers to make sure that the units are consistent. This is 173.88 kilojoule per kilogram. All right. So you need to ensure that you convert the pressure from bar or megapascal to kilopascal. The conversion units are again given in the property tables that you have on the blackboard. So HF plus specific volume. So VF is this at a pressure of 0.08 bar. Make sure that you're multiplying with, you're dividing by 1000 or multiplying with 10 power minus 3. Okay, so this is something that you have in the VF times 10 power minus 3 is equal to this value, right? Sorry, 10 power 3 is equal to this value 1.0084 or whatever given in the property table. So VF is this value divided by 1000. So make sure that you always are dividing. Don't just use this value directly from the table. Look at the title as well for VF as we discussed before. And then once you have VF, it's simply delta P, and this is what we're taking in megapascal, but we can't use megapascal because we want to be consistent in terms of the units. The units for enthalpy are kilojoule per kilogram, so we need to convert that into kilopascal, and we do that by multiplying by 1000. All right. So once you have plugged in all these numbers appropriately, this is what it comes out to be. The work input of the pump is simply 8 kilojoule per kilogram, right? So you're sort of compressing liquid from 0.08 bar, which is like smaller than atmospheric pressure, right? For reference, atmospheric pressure is about 1 bar. We're compressing liquid water from 0.08 bar to 80 bar, okay, from here to here. And for this huge amount of compression that we are doing, the work input that we need to provide is pretty small, of only 8 kilojoule per kilogram, right? So this is pretty interesting. Of course, this is small per unit mass when you consider the mass of water that we want to pump, that we want to compress. It certainly becomes larger, but on the whole, as compared to the enthalpy, it's sort of pretty small. Okay, so H4 is simply 181.94. Now we have everything that we need. We have enthalpies at the four states. We can go ahead and determine the thermal efficiencies. Okay, so the thermal efficiency, for the thermal efficiency, we need the work output for the turbine, the work input for the pump, which we have already calculated, and the heat input to the boiler. Okay, so these are all going to come from the enthalpies. And we have all the values now, H1, H2, H3, and H4. So it's a matter of just plugging into this equation right here. Okay, so this is something that we can plug in the numbers. We have H1 and H2. The second part we calculated, H1 and H4. Again, we have the numbers. So these are the different numbers. You can plug them in, and the efficiency comes out to be 37.1%. Not very high, but I mean, certainly sort of it's sort of somewhere in the average range. So we'll have to figure out ways to improve this, and before we can think of ways to improve this, we'll have to see how bad is it as compared to the Carnot cycle efficiency for the same temperatures, right? Once we do that, we'll have a better idea, and we'll see how far we are from the ideal case or from the reversible cycle, and we'll see how far we can go up. So I'll stop here. If you have any questions, let me know. Otherwise, that's the end of the class.